The electrical industry has long used the term neutral to refer to the grounded conductor. This has become common practice due to its brevity and ease of use. However, grounded conductor is the technically correct term, especially in single-phase circuits, while neutral specifically applies to multi-phase systems. There's an ongoing discussion about whether to fully transition to using GC as an abbreviation for grounded conductor to improve accuracy and reduce ambiguity. Let's examine the arguments for and against this change. Firstly, clarity. GC unambiguously refers to the grounded conductor, eliminating confusion with the neutral conductor in multi-phase circuits. This is particularly important in technical documentation and training materials, where precision is paramount. Secondly, conciseness. GC is a much shorter and easier term to use than grounded conductor, which can be cumbersome in writing and conversation. Thirdly, consistency. Using a consistent term helps avoid miscommunication and promotes better understanding among electrical professionals. Now let's consider the cons of switching to GC. Firstly, familiarity. Neutral is a widely used term in the electrical industry. Changing to GC may require a period of adjustment and re-education for many professionals. Secondly, potential for misinterpretation. Some individuals may interpret GC as ground check or associate it with other unrelated terms, which could lead to confusion, especially among those not deeply familiar with electrical terminology. Thirdly, lack of universal acceptance. The use of GC may not be universally accepted or understood, particularly among non-electrical professionals such as contractors, building inspectors, or homeowners. Some industry experts advocate for using the correct term GC to ensure accuracy and precision in technical communication. They argue that clarity and conciseness are vital for effective communication in the electrical field and that standardization promotes understanding and reduces the risk of errors. Others suggest a more cautious approach, recognizing the widespread familiarity and ingrained use of neutral. They emphasize the potential for misinterpretation or resistance to change within the industry. A balanced approach involves using GC in technical documentation, training materials, and professional communications, while allowing for a gradual transition to avoid confusion. This could involve providing clear explanations and definitions of GC alongside the more familiar term neutral during the transition period. It is essential to acknowledge that neutral remains the correct term when specifically referring to the neutral point in multi-phase circuits. Therefore, the recommendation is to adopt GC for grounded conductor in technical contexts such as documentation and training. This helps promote accuracy and reduce ambiguity. Simultaneously, allow for a transition period and provide clear explanations to minimize confusion. It's crucial to maintain the correct use of neutral when referring to the neutral point in multi-phase circuits. By implementing this approach, the electrical industry can gradually improve the accuracy and clarity of its terminology while minimizing disruption and confusion. In summary, the key considerations are promoting accuracy, minimizing confusion, and allowing for a gradual transition. In more detail, focusing on the technical aspects, the grounded conductor, often mistakenly referred to as neutral in single-phase alternating current or AC circuits, serves a critical function in ensuring electrical safety and proper system operation. Its primary role is to provide a low-impedance path for fault current to return to the source, which facilitates the operation of overcurrent protection devices like circuit breakers or fuses. This rapid clearing of faults minimizes the risk of electrical shock and fire hazards. To understand the significance of the grounded conductor, it's essential to differentiate it from the equipment grounding conductor. The equipment grounding conductor provides a path for fault current from non-current carrying metallic parts of equipment back to the source. This helps to prevent dangerous voltage from appearing on equipment enclosures, reducing the risk of electric shock. The grounded conductor, on the other hand, is intentionally connected to the neutral point of the power source, typically at the service entrance. This connection ensures that the grounded conductor is at or near 0 volts potential relative to ground. In a properly functioning electrical system, the grounded conductor carries current only during normal operation due to imbalances in the load. However, during a ground fault, It provides a low impedance path for the fault current to flow back to the source, causing the overcurrent protection device to trip and energize the circuit. The National Electrical Code, or NEC, Article 250 provides detailed requirements for grounding and bonding electrical systems. These requirements are designed to ensure electrical safety and minimize the risk of electrical shock, fire, and equipment damage. Some key aspects of NEC Article 250 related to the grounded conductor include firstly, grounding electrode system. The NEC specifies the requirements for the grounding electrode system, which provides a connection to the earth. This system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes. Secondly, grounding electrode conductor. The grounding electrode conductor connects the grounding electrode system to the grounded conductor at the service entrance. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the service entrance conductors. Thirdly, main bonding jumper. The main bonding jumper connects the grounded conductor to the equipment grounding conductor at the service entrance. This connection ensures that all metallic parts of the electrical system are at the same potential, reducing the risk of electric shock. Fourthly, system grounding. The NEC requires that certain electrical systems be grounded, including alternating current systems with a voltage of 150 volts to ground or less. This grounding provides a stable reference point for the electrical system and helps to protect against voltage surges. Fifthly, grounded conductor identification. The grounded conductor must be identified by a continuous white or grey outer finish. This helps to distinguish it from ungrounded conductors, which are typically black, red, or blue. The grounded conductor plays a critical role in electrical safety and system operation. By providing a low impedance path for fault current, it facilitates the operation of overcurrent protection devices and reduces the risk of electrical shock and fire hazards. The NEC provides detailed requirements for grounding and bonding electrical systems, which are designed to ensure electrical safety and minimize the risk of electrical hazards. In addition to the general requirements for grounded conductors, there are specific rules for sizing and installing them in different types of electrical systems. For example, in a single-phase, 3-wire system, the grounded conductor must be sized to carry the maximum unbalanced load. This is the load that would exist if all of the loads on one leg of the circuit were energized while none of the loads on the other leg were energized. The NEC provides guidance on calculating the unbalanced load in different types of occupancies. In a multi-wire branch circuit, which consists of 2 or more ungrounded conductors and a grounded conductor, the grounded conductor must be sized to carry the neutral current. The neutral current is the current that flows back to the source on the grounded conductor due to imbalances in the loads on the different ungrounded conductors. The NEC requires that the grounded conductor in a multi-wire branch circuit be sized to carry the maximum neutral current that could exist under normal operating conditions. The grounded conductor must be properly installed and terminated to ensure its effectiveness. It must be securely connected to the grounding electrode system and the equipment grounding conductor. The connections must be made using approved connectors and methods. The grounded conductor must also be protected from physical damage. It should be run in conduit or other protective raceway where it is exposed to mechanical stress. In older electrical systems, the grounded conductor may not have been properly installed or maintained. This can create a dangerous situation as the grounded conductor may not be able to carry fault current effectively. If you suspect that the grounded conductor in your electrical system is not properly installed or maintained, you should contact a qualified electrician to inspect and repair the system. They can ensure that the grounded conductor is properly sized, installed, and terminated, and that it is providing a safe and effective path for fault current. It's also important to understand the concept of impedance in relation to grounded conductors. Impedance is the total opposition to current flow in an alternating current circuit. It consists of resistance, which opposes current flow in a direct current circuit, and reactance, which opposes changes in current or voltage due to inductance or capacitance. A low impedance grounded conductor is essential for ensuring that fault current can quickly and easily flow back to the source. This allows the overcurrent protection device to trip quickly, minimizing the risk of electrical shock and fire hazards. The impedance of the grounded conductor can be affected by several factors, including the size and material of the conductor, the length of the conductor, and the quality of the connection. A larger conductor will have lower impedance than a smaller conductor. Copper conductors typically have lower impedance than aluminum conductors. A shorter conductor will have lower impedance than a longer conductor. Poor connections can significantly increase the impedance of the grounded conductor. Regular inspection and maintenance of the grounded conductor are essential to ensure that it remains in good condition and can effectively carry fault current. This includes checking the connections for tightness and corrosion and inspecting the conductor for physical damage. If any problems are found, they should be corrected immediately by a qualified electrician. The grounded conductor is a vital component of any electrical system. It plays a critical role in ensuring electrical safety and protecting against electrical hazards. By understanding the function of the grounded conductor, the requirements for its installation and maintenance, and the importance of low impedance, you can help to ensure that your electrical system is safe and reliable. The transition from using neutral to GC is not merely a matter of semantics. It's about promoting a more precise understanding of electrical concepts and improving communication among professionals. While the change may require some adjustment, the long-term benefits of increased clarity and reduced ambiguity are well worth the effort. One practical approach to facilitating this transition is to incorporate the use of GC into electrical training programs and apprenticeship programs. This will help to ensure that future generations of electricians are familiar with the correct terminology and understand the importance of using it consistently. Another important step is to update electrical codes and standards to reflect the preferred use of GC for grounded conductors. This will provide a clear and consistent message to the industry and help to promote wider adoption of the term. In addition, manufacturers of electrical equipment can play a role by labeling equipment and components with the correct terminology. This will help to reinforce the use of GC and reduce the likelihood of confusion. Ultimately, the success of this transition will depend on the willingness of electrical professionals to embrace the change and adopt the correct terminology in their daily work. By making a conscious effort to use GC for grounded conductors, we can all contribute to a more precise and safer electrical industry. Remember, the grounded conductor is not just a wire. It's a critical safety component that plays a vital role in protecting people and property from electrical hazards. By using the correct terminology and ensuring that it is properly installed and maintained, we can help to ensure that our electrical systems are safe and reliable for years to come. Considering specific applications, think about residential wiring. In a typical 120/240 volt single-phase residential electrical system, the grounded conductor, often referred to as the neutral, plays a critical role. It's connected to the center tap of the transformer supplying power to the home and provides a return path for current from the 120 volt circuits. It's essential that this conductor is properly sized and connected to the grounding electrode system to ensure safety. In commercial buildings, which often utilize three-phase power systems, the grounded conductor, or neutral, serves a similar purpose. However, in these systems, it's even more important to distinguish between the grounded conductor and the equipment grounding conductor. The grounded conductor carries the unbalanced current from the three phases, while the equipment grounding conductor provides a path for fault current. Improper grounding and bonding in commercial buildings can lead to significant safety hazards. Industrial facilities often have complex electrical systems with a variety of voltage levels and equipment. In these environments, it's crucial to have a clear understanding of the role of the grounded conductor and the equipment grounding conductor. The grounded conductor must be sized to handle the expected and balanced load, and the equipment grounding conductor must be sized to provide a low impedance path for fault current. Regular inspections and maintenance are essential to ensure the safety and reliability of the electrical system. In healthcare facilities, electrical safety is of paramount importance. Patients are often connected to sensitive medical equipment, and even a small electrical shock can have serious consequences. The grounded conductor and the equipment grounding conductor must be installed and maintained to the highest standards to minimize the risk of electrical hazards. Isolated power systems are often used in critical care areas to provide an extra level of protection. In agricultural settings, electrical systems are often exposed to harsh environments and subject to physical damage. The grounded conductor and the equipment grounding conductor must be protected from corrosion and physical damage to ensure their effectiveness. Ground fault circuit interrupters, or GFCIs, are often required in agricultural buildings to protect against electrical shock hazards. Renewable energy systems, such as solar photovoltaic or PV systems and wind turbines, also require careful attention to grounding and bonding. The grounded conductor and the equipment grounding conductor must be sized and installed to meet the specific requirements of these systems. The NEC provides specific guidance on grounding and bonding renewable energy systems. In all of these applications, it's essential to use the correct terminology and to follow the requirements of the NEC to ensure the safety and reliability of the electrical system. While the transition from using neutral to GC may seem like a small change, it can have a significant impact on the clarity and accuracy of electrical communication. By embracing this change and using the correct terminology, we can all contribute to a safer and more efficient electrical industry. So, remember, GC for grounded conductor, and let's work together to make this transition a success. By using the term GC for grounded conductor in technical documentation, training materials, and professional communication, electrical professionals can promote accuracy and reduce ambiguity and allow for a transition period and provide clear explanations and definitions to avoid confusion and allow for the use of neutral when referring to the neutral point in multi-phase circuits.